Okay, so I apologize. The print is really small on this, and I have trouble myself reading it, but I didn't give you the... Oh, I gave you the practice? Oh my gosh, sorry. All right, so we're really starting now. So looking at your notes that you actually have in front of you now, you'll see two different graphs, and you might notice those shapes from the Desmos activity that we did. These are exponential decay and exponential growth. Can anybody think of something that grows exponentially? Plants? It might. Some of them might, for sure. What else? Have you ever seen a graph like that goes up so fast?
It's like a plane that takes off.
It kind of looks like that, doesn't it? So a lot of times populations grow exponentially. Is that what you're going to say, Kate? Yeah. So a lot of times populations are going to grow exponentially. Look at the decay one on the left. Can anybody think of something that decays exponentially like that?
Trees.
Isn't that what you said for the other one? All right. Well, one thing for sure is like radioactive decay, like the amount of radioactivity in something. Another one is carbon-14. Does anybody know what carbon-14 is used for? What's that? Yeah, it's for dating, right? It's for carbon dating. So if you want to know how old a fossil is or how old a tree is, you can use carbon-14 dating to find out how long it was since it was living, basically. So because the amount of carbon-14 will decay exponentially in a predictable pattern. So there are a lot of things in this world that are exponential decay or exponential growth. Looking at the equations, look at the first part of the equation. F of x equals b to the x. F of x equals b to the x. It looks like the same equation. So to figure out what's different, you're going to need to look below that. Look below that. They have the same equation. It's going to be decay if your b is between 0 and 1. What are some examples of numbers between 0 and 1? Okay, so b could be 0.5. What else could it be? So b could be 0.5, 0.3. How about a fraction? Go ahead, Gabby.
7/16.
7/16. It's a good fraction. All right, so if b is a number between 0 and 1, like 0.5, 0.3, 7/16, then you're going to have exponential decay. And then over here it says if b is greater than 1, we're going to have exponential growth. So what are some numbers that are greater than 1? 2 and what else? 3. So b could be 2. B could be 2 or 3. Or how about a fraction that's greater than 1? What if we just do the reciprocal of Gabby's? 16 over 7, right? 16 over 7 is a fraction, but it's greater than 1. So that would still give us exponential growth. Okay? Let's talk about the asymptote. Exponential functions have a horizontal asymptote. Raise your hand if you have seen an asymptote in a graph before. Nobody? All right. Welcome to your first. A horizontal asymptote is an essential part of the graph, but it's actually the part that the graph is not existing in, not the part that it is existing in. It's telling you that there is this invisible horizontal line here that your graph is going to get closer and closer to, but not actually touch it, which means our graph can never have a y value of 0. It's this dashed line down here, okay? So the equation of the asymptote is y equals 0. And because we have an asymptote at y equals 0, that means that we're not including 0 in our range. Our domain is still negative infinity to infinity, but not our range. So our range is going to start right after 0, not including 0. So notice I'm going to use a parentheses instead of a square bracket on the 0 to show that The graph gets really close to 0, but they can never touch, okay? It's almost like a Valentine's love story, right? They get so close, but they'll never meet. All right, over here, domain and range are the same. So same asymptote, domain and range. So the first two questions are just asking if you were paying attention. If the B is between 0 and 1, would that be growth or decay? Anybody else want to vote on that? Decay? 2 votes for decay? Okay. Okay, decay. What kind of function is created when B is larger than 1? That would be a growth. So down below, we're just going to be identifying parts of the equation. So the number that is being raised to the x power is either called the growth factor or the decay factor. And then the rate is going to be the difference between the number and 1. The rate is going to be a positive number. So in this case, to find the rate, it says 1 plus 0.25 gives you 1.25. I would prefer to find it by just subtracting 1 from it. So in this case, the rate is 1.25 minus 1 to get a positive answer. And then in this case, it's going to be 1 minus 0.97. All right, sorry. So I said 1 minus 0.97, which is how much?
0.03.
Let's think about that. Which is it? 0.03? Okay. 0.03. And that's the rate. So in these problems, what we're doing is we are going to identify if it's growth or decay, what the factor is, and then what the rate is. And we'll do A together. So A, what is our B value that we're looking at? Which number, the 5 or the 2/3?
2/3.
Beck says 2/3. Anybody want to agree with 2/3 or give a different answer? I have one agreeing with 2/3. Is 2/3 the B value that we're looking at? Okay, it is. So 2/3 is between 0 and 1. So would that be a growth or a decay? Decay. So we're going to say that the decay factor is 2/3. Okay, to find the rate, I'm going to subtract that from 1. So 1 whole minus 2/3 is what fraction?
1/3.
Very good. Very good. So remember, 1 whole is 3/3. And if I subtract 2/3, I'm left with 1/3. That's my rate. All right, we're going to do C together, and then I'm going to let you guys work on B and D. Looking at C, what is different here? What do you notice that's different?
There's an exponent.
There's an exponent. How's the exponent different from the previous exponent?
It's negative.
Yeah. So negative exponents are kind of not usually used. So we change that to a positive, but the way we change it to a positive, you need to think back 2 units. What did we do when we had a negative exponent?
Over something.
Yeah, so basically it would move to the other part of the fraction, right? So if this is 3/1, then it would become 1/3. It's basically the reciprocal. So when you have a negative exponent, so if x is negative, take the reciprocal of the base, and then you can have a positive exponent. So then it becomes 10 times 1/3 to the x. So now that we have a positive x, we can evaluate it. Is it growth or decay?
Decay.
Okay. So 2 people are processing the lesson. Other people can answer too, all right? So the base is 1/3, which is between 0 and 1. So that means that this is decay, and our decay factor is 1/3. And for the rate, just subtract it from 1. So 1 is 3/3. 3/3 minus 1/3 is 2/3. Fractions. Okay. All right, so you guys work on B and C for a minute. So B is growth or decay? What'd you guys get for B, growth or decay?
No, remember that it says if it's more than 1, then it's a growth.
This is less, no, because I don't I'm basing it off of this one.
I know, but you put 1/4. It's 4/1 if you're
All right, growth factor, did you put 3/2? Good. And then for the rate, we subtract 1, and Ahmed, what did we get? 1/2. Very good. If anybody preferred using decimals there, they did work fine. So you could say that your growth factor was 1.5 and your rate was 0.5. That works too. All right. For D, we can change 0.25 to be what fraction?
1/4.
True. Yeah, so 1/4, right? So remember, 0.25 means 25 cents. 25 cents is called a quarter because it's a quarter of a dollar. So if you have trouble with that decimal to fraction conversion, you can think of it that way. But now I have a negative exponent, and now I can take the reciprocal. What's the reciprocal of 1/4? 4/1. Very good. 4/1 is the same as 4, so I'm just going to write 4. So now my B value is 4, which means it's which one, growth or decay? Growth, yeah. So my growth factor is 4. And my rate is going to be what? What'd you guys get for the rate?
3/1.
Good. All right, so that's just identifying parts of the equation. On the back, we're going to do some regression. So you're going to need your computer. If you put your computer away, we're going to need that. Because think back to the project that we did about the sun, how we did a regression on those points to make a quadratic curve of best fit. We're going to make some exponential curves of best fit here. So on the back, we're going to do problem 1. And I want you to open up Desmos and put those points into your table. All right, so once you have these points in, let's go back and read the context of the problem. A cup of soup is left to, on a countertop to cool. The table gives the temperature in degrees Fahrenheit of the soup recorded over a 10-minute period using an exponential model. So it's telling us they want us to use the exponential model. Write an equation for the curve of best fit, and then estimate the temperature for 5 minutes. So we're going to enter what is next to the word exponential on your paper, above it. We're going to enter that underneath the table. Y1 tilde A times B raised to the x1. And then you're going to write these numbers for A and B on your paper. On your paper? Underneath number 1. We're working on number 1. Just leave some space because there's more to write.
So the RT parameters?
Just the A and B. Okay, so we should have the same A and B value because we did the same problem. This is what I got. And when you write your equation, you don't write it in this way that tells Desmos it's a regression. You write it normally in the y equals A times B to the x way, like this. So I'm going to write y equals 180.325 times 0.953959 raised to the x. So the x is your exponent. And the reason why we write this equation down is because now we can use this to make predictions. So you'll notice 5 minutes is not on my chart. And if I want to know the temperature after 5 minutes, I'm going to substitute 5 for the x. So you're going to put that into Desmos. 180.325 times 0.953959 raised to the 5. So put that into Desmos, see what you get.
142.46.
Okay, does that make sense looking at your table of values? Because it should be between the 4 minutes and the 6 minutes. Yeah? Okay. All right, write it on your paper. I'm going to do the problem too. So what we have on our paper is what we're typing into Desmos. 180.325 parentheses 0.953959 then raised to the 5th. All right, I think I'm getting the same thing that you guys got. So down here is where I did that. And I got 142.5 degrees about. Degrees Fahrenheit, because there exists a scale called Celsius too. Okay. All right, we're going to start the next one and then we'll finish it after lunch. In the next one, we're talking about the NASDAQ. Listed are the NASDAQ stock index at the end of February, starting with 1992. Using an exponential model again, so still exponential. Write an equation for the curve of best fit, then estimate the year the closing price will reach $9,500. So this time they're suggesting that we use 0 for 1992. So that would mean that we're going to do years after 1992 for our x. Years after 1992. So how many years after 1992 is 1994? 2. And then 1996? That's 4 years after, right? Notice they're going up each time by 2 years until we get to 8 years after. So you're going to use those for your x instead of the actual years, and then you'll use these for the y. And take note if you make a new table. Let me just show you. If you make a new table in this one, it's going to label it x2 and y2, and you'll use that in your regression. If you don't want to have to worry about that, you can just open a new tab for Desmos, and then you'll be at x1 and y1 again. All right, so we're going to enter that. We're going to try to put the regression in, see how much we can get done before lunch. And then enter your regression equation if you get the table in. $4,696. Okay. Remember, you can hit the zoom fit magnifying glass here and see the shape. And then you want to write down your values for A and B, and then write the equation with those. Yes? So in the equation, the exponent is x. But then, oh, I see what you're saying, like when you answer the actual question. We're going to work on answering the question afterwards because this time we're substituting a y value and not an x value. Yeah. Okay, so for number 2, we did use years after 1992. So this was 0 years after, 2 years after, 4 years after, etc. We put the table with this x column and this y column into Desmos, and when we found our exponential curve of best fit, this is the A and the B value that we get. Now this time it asks us when the closing price will reach 9,500, and that is a y value. So we need to know when the y is equal to that. Later in this unit, we're going to learn how to solve an equation for an x as your exponent, But for now, we haven't learned that yet. So in order to find out when the y is 9,500, we're going to use Desmos. So let me pull your Desmos right back up. And this is the right one. So we're going to put in y equals 9,500. And you'll need to zoom out just a little bit to find it. And then that looks like it's about 10 years after 1992. So that would be about the year 2002.